Good morning, students. Next, our experiment is Thevenin's theorem. This is our kit. So in this kit, you remember here R1 resistance is 82 ohms and R2 resistance is 150 ohms and R3 resistance is 47 ohms. Already these three resistances are fixed in this particular kit. Okay, by using these three resistances only we are going to do a theoretical calculation and as well as practical values observation. Okay, so here also we have a different types of resistances, but here we are unable to take these resistances. Here already fixed these resistances, but these resistances we are going to use for a load purpose only. We are going to use these resistances, either 150, 120, 100, 75, 47 for load purpose only. Okay, so then we are going to do a theoretical calculation first, then we'll come back for practical observations. You remember here these are the theoretical calculations for Thevenin's theorem. Okay, you remember here Thevenin's theorem statement. Thevenin's theorem states that only a two-terminal linear network having a number of voltage sources and resistances can be replaced by a simple equivalent circuit consisting of a single voltage source in series with a equivalent resistance. So this is a very huge statement, but that statement I have simplified. I have written two lines. You remember here voltage source in series with Thevenin's and load resistance. You observe here one diagram is there. So related to this diagram only I have said this statement. So this is a voltage source. This voltage source in series with Thevenin resistance and as well as load resistance. That is the statement here simply. Voltage source in series with Thevenins and as well as load resistances. Okay, so simply already I have shown kit. So related to that kit we have circuit diagram here. Power supply we are going to take a 0 to 15 volts and R1 resistance 82 and R2 resistance 150 ohms and R3 resistance 47. Here we are going to take a load resistance 100 ohms. So we have a different types of resistances in that particular kit, but we are going to take load resistance only 100 ohms. Okay, so here I am going to take a 15 volts input voltage. For this 15 volts only I am going to do a calculation part. So in Thevenin's theorem and as well as Norton's theorem, in both the calculations we are calculating only three values majorly. So in Thevenin's theorem first we are going to calculate IL load current and Thevenin voltage V Thevenin and Thevenin resistance R Thevenin. Okay, so finally we are calculating load current IL, that is equal to V Thevenin by R Thevenin plus RL. Okay, so here V Thevenin equal to Thevenin voltage and R Thevenin equal to Thevenin resistance, RL equal to load resistance. So before going to find out this load current, first we need this V Thevenin and R Thevenin. RL already we have taken 100 ohms. That one is already fixed. Okay, but we need to find out what is the V Thevenin voltage and R Thevenin voltage by using different conditions and calculations. So first we need to calculate a V Thevenin calculation. Okay, so conditions for V Thevenin calculation, we need to find out V Thevenin calculation. We have majorly two conditions. The first one is load resistance in open circuit condition. So you observe in this particular circuit diagram, load resistance already I have open circuited. Okay, then we will go to find out the equivalent resistance in this particular network. So whenever we are taking open circuit at this load end, there is no any flow of current through from this node to this resistance 47 ohm resistance. So whenever we need to find out Thevenin, first condition is load resistance in open circuit condition. So already I have open circuited a load resistance. Whenever I can open this load resistance, then automatically there is no any flow of current through this resistance. It's mean whenever reach the current at this particular node, there is no any flow of current through this resistance, because whenever we can do a open circuit here in the sense, so this entire loop will be a open circuit. So this entire loop will be a open circuit in the sense there is no any flow of current through this loop. So simply in open circuit condition current is 0. So that is only the reason we are not consider this 47 ohm resistance. We are calculating based on these two resistances only equivalent resistance. You can observe that one in here. Okay, so here Thevenin formula, Thevenin equal to V into R2 by R1 plus R2. So what are R1 and R2? Here you remember R1 is a 82 ohms and R2 is a 150 ohms. Okay, so this 47 ohm resistance will not consider because of open circuit condition. So here R2 is 150 and R1 is 82. So we can substitute here. Already we have taken voltage source V equal to 15 volts. So Thevenin equal to 15 volts into 150 by 150 ohms plus 82 ohms. So that is equal to, we can get it 9.69 volts. That is a Thevenin voltage. Then we are going to calculate R Thevenin calculation. So conditions for R Thevenin calculation: first, load resistance in open circuit condition. So if any voltage sources are there in the network, all the voltage sources we are going to do a short circuit condition. If any current sources are there in the network, all the current sources are in open circuit condition. So in given below you can observe we have only voltage source, so that's why we can do that voltage source in short circuit condition. So by using circuit reduction technique we can find out the total equivalent resistance in this network simply. Okay, first condition, according to first condition I have done open circuited load resistance, and according to second condition voltage source in short circuit condition. There is no any current sources here, you remember. So by using circuit reduction technique I am going to calculate equivalent resistance here. So where we done open circuited where we done a short circuit, from that side too we can calculate equivalent resistance. So you can observe here. Okay, so we done short circuit condition here. That's why R1 and R2, these two are in parallel. Because of that R1 into R2 by R1 plus R2. So these two resistances are in series with this resistance. That's why we can finally take R3 resistance. You remember here. R Thevenin equal to R1 into R2 by R1 plus R2 plus R3, because these two resistances are in series with R3 resistance. Then I can substitute all the resistance, 82 into 150 by 82 plus 150 plus 47. We can get it R Thevenin equal to 100.017 ohms. Then finally IL is equal to, so we have a Thevenin voltage and R Thevenin voltage and RL load resistance. So Thevenin voltage we can find out, that one is 9.69 volts. R Thevenin we can find out here 100.017, and our load resistance equal to 100 ohms. So I can substitute all the values. We can get it load current equal to 0.048 amperes. This is the final load current value. Okay, so you can observe here we have a practical diagrams here. Based on these practical diagrams only we will going to observe the all the values. So V Thevenin value and R Thevenin value and load current values. So according to these practical circuit diagrams only we will be going to connect in the kit. So here you remember for source voltage, how much of source voltage we have taken, we need to see by observe by using this voltmeter. It's mean across source we can take one voltmeter. That voltmeter range is 0 to 20 volts, and remaining resistances R1 is 82 and 150 and 47. All three resistances are same. So according to first condition, whenever we can find out V Thevenin, we can do a open circuit load resistance. Then here I have done open circuit load resistance here. Where we done a open circuit, so that place I have taken one voltmeter to find out the Thevenin voltage. And the next one R Thevenin find out. So here according to condition, so voltage source I have done a short circuit, and where we need to find out the Thevenin resistance, at that particular case condition I will be going to take one multimeter. By using that multimeter I will be going to measure R Thevenin resistance simply. So it means source voltage I will be going to short circuit and take one multimeter. So in that multimeter I will be going to take a resistance, R Thevenin resistance. And here you remember finally we can observe load current here. That load current same circuit. So for a source voltage measurement purpose I have taken one voltmeter, and these three resistances are same, and I need to measure the load current by using one ammeter. That ammeter I will be going to take a 0 to 200 milliamperes. Okay, so you remember here 0 to 200 milliammeter, because here we got load current is very less current. That one is 0.048. That's the reason only I have taken here milliammeter, and load resistance is 100 ohms remains same. Then we will go for practical values observation. So this is our circuit. You remember here Thevenin's theorem kit. So here you remember already one DC circuit is there. So this DC circuit will be going to convert AC into DC, but this circuit there may be a little bit damage. Because of that I have taken one regulated power supply. This regulated power supply is useful to convert AC power supply into DC. That DC only I will be going to connect here at input condition. So input voltage I am going to take here, and then first we need to find out V Thevenin voltage here. So according to that here load resistance in open circuit condition, where we done a open circuit condition, that particular case I have to connect one voltmeter. That voltmeter also DC voltmeter. That range of DC voltmeter is 20 volts DC. So that 20 volts DC I will be going to where I have done a open circuit load resistance. That place I will be going to put this voltmeter. Okay, simply. So remaining all 82 R1 resistance 82 and R2 resistance 150 and R3 resistance 47, remaining is same. Then I will be going to turn on the regulated power supply. Here you have to observe regulated power supply voltage is 15 volts I have taken. So you remember here what is the voltage, Thevenin voltage we got 9.70. So according to our theoretical calculations, you remember we got V Thevenin voltage is 9.69, because here little bit small input voltage is high. Because of that we got little bit variation. You remember right now 9.64 volts or a 59 volts. Okay, this is a Thevenin voltage. Then we can find out R Thevenin. So for find out R Thevenin condition, it's simply voltage source. I mean input voltage source. We can do short circuit, and then we can connect one multimeter across these two terminals. Then we will find out R Thevenin. That's why I am going to turn off the power supply here. Then remove this power supply. Then I will be going to short circuited this source voltage. The source voltage I have short circuited. Then I will be going to take one multimeter here. You remember, this is a multimeter. So I have done for both voltage and resistance measurement. I have taken this pin and common terminal I have connected. So then I am going to connect here where we have done an open circuit in Thevenin circuit. That place only we can put it one multimeter. So we can keep that multimeter in ohms only. So these ohms only find out the resistance. So you remember, short circuited, voltage source is short circuit, there is no any current sources here, and where we done open circuit, that place I have taken one multimeter resistance. So we can get it, resistance is 102.2 ohms, but theoretically we can get it here. Thevenin resistance is 100.017, just a 2 ohms little bit variation. So compared to practical and theoretical, it's not a huge difference, no need to bother about for that. And then we will go for find out the load current. So according to load current, we need to connect this circuit. And finally, third value we need to find out load current. So for that load current, we are taking a 15 volts source voltage here. So by using one voltmeter, we can measure that 15 volts, how much of source voltage we have taken. Remaining all the resistances are same here. You remember, there is no any change, all the resistances. And you remember, for 47 ohm resistance, second terminal will be going to connect for ammeter first terminal. You observe here, 47 ohms, second terminal will be going to connect for DC ammeter. That DC ammeter also 200 milli ammeter, DC ammeter. So I will be going to connect for ammeter first terminal, and the second terminal of ammeter will be going to connect for load resistance first terminal. Load resistance. So load resistance already we have taken 100 ohm resistance. So already I said so many times, here load resistance is 100 ohms. That 100 ohms I have connected. Second terminal of ammeter will be connected for first terminal of load resistance, and second terminal of the load resistance will be going to connect for circuit. Okay, circuit in the sense for a negative terminal. Then I will be going to turn on the power supply. You observe here, 15 volts input source voltage, and then you can observe here in ammeter 200 milliammeter DC we have taken. So we got 47.6 amps. So it's mean 47.6 into 10 to the power of minus 3. It means simply 0.0476. So we got theoretically also load current 0.048. We got 0.047 practically, but theoretically we got 0.048 amperes. Okay, so practically and theoretically proved Thevenin's theorem. Okay, thank you very much.